In this video, I'm going to work through a few examples of finding the derivative of relations that are implicitly defined. The first example we're going to look at is the equation of an ellipse, x squared minus xy plus y squared equals 7, and that ellipse is pictured right here. To find the derivative of this function with respect to x, and remember, if we want to find the slope of the function, we have to find dy dx. So to find dy dx, what we are going to do is we are going to take the derivative of each term with respect to x, and we're going to use a chain rule where appropriate. In fact, we're going to show that we're going to use a chain rule with every term, even if we don't necessarily need to. So the derivative of the first term, x squared, with respect to x will be 2x, and since we took the derivative of x with respect to x, we'll write dx dx. The second term, we're going to have to use the product rule since we have the function x times the function y. So we have a function times a function, and that means we're going to have to use the product rule. So to do that, we're going to take the derivative of the first. The derivative of the first would be the derivative of x, which is 1 times dx dx. Remember, we're taking the derivative of x with respect to x times y, plus the first, x, times the derivative of the second, which is 1, and we're taking the derivative of y this time with respect to x, so dy dx, and plus the derivative of the y squared term, which will be 2y, and then dy dx, since we're taking the derivative of a function in terms of y with respect to x. That's again using the chain rule, and that's equal to 0, which is the derivative of any constant. Simplifying this a little bit here, we have dx dx, which is 1, dx dx, which is 1, and then we have dy dx in a couple of different places. We have it here and here, and that's what we want to get by itself. So rewriting this to simplify, we get 2x minus y minus x dy dx plus 2y dy dx is equal to 0. Now, to get dy dx by itself, what we're going to have to do is we're going to have to factor it out of these terms once we've gotten them by themselves. So we're going to collect all the terms with dy dx in them on one side of the equation, and all the other terms we're going to move to the other side of the equation. So we're going to have to subtract 2x from both sides of the equation and add y to both sides of the equation. And so what we end up with then is negative x dy dx plus 2y dy dx is equal to y minus 2x. And we get that just by adding y to both sides and subtracting 2x from both sides. At this point, we can factor the dy dx from both of these terms, and what I'm going to do in the interest of space is I'm going to do that on this same line here. So had we done that in that step, we would have dy dx times the quantity negative x plus 2y. And just for cleanliness, we might write this expression as 2y minus x if we wanted to. The last thing we need to do now to get dy dx by itself is divide by the negative x plus 2y. So we get y minus 2x over negative x plus 2y. And with the positives and negatives, we could write it a few different ways. We could write it as y minus 2x over 2y minus x. Depending on what you do, it's possible to factor out a negative 1 on the top and the bottom, and we would have 2x minus y over x minus 2y. But this would be an acceptable answer and a free response as long as it's equivalent to the correct answer, which of course it is. We could also take this same ellipse here and use our result from the last one. Remember, we have the derivative of y with respect to x is equal to y minus 2x over 2y minus x to find the slope of a line that is tangent to this ellipse at a particular point. So we could use it to find the slope of that line right there and ultimately find the equation of that line. And all we have to do that is plug -1 in for x and 2 in for y in this expression here. So anywhere we see a y, we'll put in a 2. Anywhere we see an x, we'll put in a -1. And so we get 2 minus 2 times -1 all over 2 times 2 minus -1. And so we end up with 4 on top and 5 on the bottom. And so the slope of that line right there is going to be 4/5. If we were interested in finding the equation of this line, we could go one step further and we could write the equation of that line using this point and this slope, and we could say y minus 2 is equal to 4/5 times the quantity x plus 1. So we have the y value, y minus the y value of our point equals the slope times x minus the x value. X minus -1 is equivalent to x plus 1. So we can use the derivative that we found originally with respect to x to find the slope of the curve at any given point, and also the equation of the curve at any given point. Let's look at another example here, and in this example we'll keep it simple. We just want to find the derivative of y with respect to x, which again, that just gives us the slope of the curve at any given point by plugging in the x and y values at that point. So we'll go term by term. The derivative of the 2y is going to be 2. But since we took the derivative of y, we're going to multiply by dy dx equals 2x times dx dx. Now, it's not a bad idea to stay in the habit of writing dx dx since we took the derivative of x with respect to x, but it's not necessary. That's just going to be 1, so we'll go ahead and leave that out. Plus the derivative of the sine of y. Remember, the derivative of sine is cosine, so the cosine of y times, since we took the derivative of y with respect to x, we need to use a chain rule and multiply by dy dx. Again, we want to collect all the terms with dy dx in them on one side, so we have 2 dy dx minus cosine of y dy dx is equal to 2x, and factoring out the dy dx, we get dy dx times the quantity 2 minus cosine of y is equal to 2x, and we can now divide by 2 minus the cosine of y to get dy dx by itself, and we get 2x over 2 minus the cosine of y. In this last example here, we'll find the first and second derivatives of the relation. So we will look for the value of dy dx and also the second derivative of y with respect to x. So we'll start by differentiating term by term. The derivative of y to the third power will be 3y squared, but since we're differentiating the variable y, we have to use a chain rule and multiply by dy dx, plus the derivative of x to the third power, which would be 3x squared times dx dx, the derivative of x with respect to x. Again, remember that's equal to 0, so we can just leave that out. And that's equal to the derivative of 1, which is a constant, and the derivative of any constant is 0. It's fairly straightforward at this point now to get dy dx by itself. I'm going to go ahead and do two steps at once. we will subtract 3x squared from both sides, and then divide by 3y squared to get dy dx by itself, and we get negative x squared over y squared. And that is the value of the first derivative. I'm going to clear the work out here so that we can have a little space to find the second derivative. So we know the first derivative is with respect to x. I miswrote that. The first derivative with respect to x is going to be dy dx, and that's equal to negative x squared over y squared. So finding the second derivative now, we'll take the derivative of that. So we have the second derivative of y with respect to x is equal to, and now we're going to have to use the quotient rule. Low d high, we'll have y squared times the derivative of the top, negative 2x dx dx, minus high d low, negative x squared, times the derivative of y squared, 2y, and again we're taking the derivative of y with respect to x there. Using the chain rule here, we have to multiply by dy dx all over the square of what's below. Y squared would be y to the fourth power. This would not be an acceptable answer in a free response section of a test because we do have to get rid of the dy dx here. All we have to do here is get rid of the dy dx, but we'll go ahead and simplify this too as much as we feel is necessary. So replacing dy dx with negative x squared over y squared and doing a little bit of simplification at the same time, we get negative 2xy squared plus 2x squared y times negative x squared over y squared all over y to the fourth. Now we've satisfied the condition that we get rid of dy dx, and this would be an acceptable answer for a free response. It would not be a bad idea to try to simplify this a little bit more. We might have to match it up with a multiple choice response. So two things that I see we can do here. First of all, this y and one of these y's will cancel with each other. So we can get rid of that, and this will just become y in the denominator. And then getting a common denominator in the numerator, we can multiply this by y over y, and we would end up with y to the fifth in the denominator. And let me take that two steps at a time here, or one step at a time, sorry. So we would get negative 2x y to the third power over y plus, and this is going to be 2x squared times negative x squared, so that's actually going to be a minus there, minus 2x to the fourth power over y, and that's all over y to the fourth. Now these two terms can be written as one term with y in the denominator, so it's going to be 2x y to the third minus 2x to the fourth all over y. And this is getting a little bit sloppy here, so let's simplify. And at the same time, I'm going to factor out a negative 2x in the numerator. So up top we get negative 2x times y to the third plus x to the third all over y to the fifth. And if you remember, we had an example before where we were able to use the original function to substitute into the second derivative here to simplify it a little bit. And here we have x to the third plus y to the third. And over here in the original function we have y to the third plus x to the third equals 1. So we can replace this part right here with 1. Let me take a moment here to clean it up. So what we end up with then is negative 2x over y to the fifth. Now again, right here we did not have an acceptable answer because we had dy dx in our answer. This right here would have been an acceptable answer in a free response section of a test. However, this is the type of question we might see in a multiple choice section where we would want to match it up with one of the choices. And likely that choice would be much more simple than what we had, and it might look like negative 2x over y to the fifth. This expression here is also more useful than this one if we wanted to go on and take the third derivative. It would be much easier to use the quotient rule once here than to go up here and use the product rule a couple of times and use the quotient rule at the same time, and that would get very complicated. So by simplifying this expression, it allows us to find even higher order derivatives much more simply if that was our desire or if we were asked to.